There are four derivatives for trig functions that you are going to be responsible for. You are going to need to know the derivative of sine, cosine, tangent, and secant. So what I'm going to do is we are going to develop from the definition of the derivatives of sine and cosine. Then we're going to use some trig relationships to find the derivatives for tangent and for secant. This is fairly trig intensive in that we do use a trig substitution that is not one that I told you you had to know. Here's the beauty part of derivatives of trig functions. You are never asked to develop the derivative of sine from the definition of the derivative. Once we go through from the definition and find out what the derivative of sine is, you just memorize that if f of x equals the sine of x, then f prime of x equals what we're fixing to develop here. But I am going to walk through it from the definition of the derivative so that you trust what I'm telling you is true. I find that a lot of math students are comfortable if they know why. Even if they never use why it's true, they're more comfortable if they know why things are true. So remember, the definition of the derivative is f of the quantity x plus h minus f of x all over h. For us, f of x is the sine of x. You can see that all I've done here is fill in the pieces of the definition of the derivative using f of x and f of x plus h. We're going to expand using good trigonometry the sine of the sum of an angle measure. It is not true, and those of you that have had trigonometry will remember, it is not true that the sine of the sum of two angle measures is equivalent to the sine of the first angle measure plus the sine of the second angle measure. In other words, many students would just like to distribute the operation of sine through the parentheses. That is not a true statement. There are product to sum or sum to product identities that are taught to trig students in a semester-long or year-long trig course. Since we don't use this identity on a daily basis or really at all when it comes to our test, it's not one that I had you know. But know that this is a trig identity, and that's all I'm doing is I'm writing the equivalent expression for the sine of the sum of two angle measures. That equivalent identity is the sine of the first angle measure times the cosine of the second angle measure. There's x, there's h. Plus the cosine of the first angle measure times the sine of the second angle measure. That is an identity. What is in this box and what is in this box are equivalent statements. And I've made that substitution because I'm still trying to factor an h out of the numerator if I can. It may not be possible, but I'm going to try. I'm going to manipulate what's going on in the numerator of this fraction as far as I possibly can until I can get to a point and evaluate this limit. Right now, if I plug in 0 and do the substitution theorem, this limit is undefined. Now what I've done is I've recognized that I have three different terms in my numerator. Here's one term, here's a second term, there's a third term. So knowing that I have a common denominator for each of these terms, I have chosen to put terms together that are alike. Both of those terms have the sign of x in them. So I have taken this term minus that term and made a fraction with its own denominator out of those. Because if I have like terms, I get to factor those out. And that's what I'm doing. Remember, our process is trying to factor things out that might cancel with what's going on in the denominator. This term does not have a sine of x in it, so I'm just leaving it as is and giving it its own denominator of h. I have factored out the common term, and you can see that what is left when I take sine of x out of that term is cosine of h. What is left here after I take sine of x out is 1. And so I've just factored the sine of x out front, and everything that has h in it, I've put right there in its own term. I've also, since this doesn't have an h in it, because h is what's in charge of what's happening here, x is not, I have factored cosine out of this term, which just leaves a sine of h, and I have grouped everything that has an h in it together. That's just algebra. That's just me manipulating what's going on inside that limit, trying to get it to a point where I can evaluate it. Again, luckily for us, we don't have to do this every time we need to know what the derivative of the sine function is. We're doing this once, and I'm being meticulous, walking you all the way through all the steps, so you trust what I tell you the derivative is. Now, remember from the main limit theorem, limits break up over multiplication. So I've broken up over the multiplication sign right there. Each has its own limit. Limits break up over addition. So I've copied that plus side down. There's another product here. And so I've broken those limits up. Each limit has its own limit notation. Now I can concentrate on each piece. If I can find what the limit as h approaches 0 of sine of x is, I can put it in those parentheses. If I can find what the outputs of this function are doing as the inputs approach 0, I can fill in this parentheses, and so forth. So that's what I'm trying to do here. That limit and that limit, I already know what those are. I can evaluate those. I can take h to 0. There is no h here. If h approaches 0, or I substitute 0 in for h everywhere in this function, I just get the function back. As far as h is concerned, this is a constant, and the limit of a constant is a constant. And we have the same thing going on here. As far as h is concerned, since there are no h's written there, that's a constant. So those two I can evaluate right now. These two, however, are a different story. If I plug in h, I still have division by 0. I can't factor an h out of the numerator. And the fact of the matter is, right now, I don't know enough calculus to evaluate those limits. So we're not going to evaluate those limits as such. We're going to go back fundamentally to what the graphs of those functions are doing. Because remember, that's what a limit is. As inputs head towards 0, what are outputs doing? And we can clearly see from this function, if we turn cosine of h minus 1 over h into the function in x and graph it, as inputs approach 0 from the left and from the right, outputs approach 0. So this limit has a value of 0. The same here. If I turn this expression into a function and graph it and see as inputs get near 0, what are outputs doing? As inputs get near 0, outputs on both sides are headed to 1. So that equals 1. So now let's fill in our parentheses with all those pieces. The sine of x times 0 plus the cosine of x times 1. The derivative of the sine of x is the cosine of x. How brilliant is that? Of all the things that the rate of change of the sine function could turn out to be, the fact that it is the outputs of the cosine function, That's amazing. So here's what you need to know. This is what you are responsible for. Given f of x equals the sine of x, you are responsible for knowing, you must know f prime of x equals cosine of x. You'll hear me when we're doing homework problems, you'll hear me bring plus signs to the party. We'll need the plus signs a little later on. So you'll hear me say things like the derivative of positive sine is positive cosine. Well, it is. That's true. That's a positive function. This is a positive function. And that becomes important later on because, as you can guess, probably in another relationship, there might be some negative signs that show up. So make sure that you understand that the derivative of positive sine of x is positive cosine of x. Now, we're going to develop in the exact same way from the definition of the derivative what the derivative of the cosine function is. You can see as well f of x plus h minus f of x all over h. I have used the equivalent and correct trig identity to substitute in there and expand the cosine of the sum of two angle measures. I have gathered like terms and factored out everything that has an x in it. And I have, either by looking at the graph or understanding that the limit of a constant is a constant, I have filled in all of the values just like we did for sine. And it turns out the rate at which the cosine function is changing is the negative sine function. So you are responsible for knowing, given f of x equals positive cosine of x, you must know f prime of x equals negative sine of x. You are responsible for knowing those derivatives. And if you know those derivatives, you can develop the derivatives of tangent and secant, the last two trig functions that you are going to be responsible for knowing the derivative of.